Okay, folks, welcome to lecture 13, the first lecture on units, and we'll be looking at working with prefixes and then simple and multi-step unit conversions. So we just take a look when sums go bad. This was a very famous kind of incident back in the 80s. So essentially, an Air Canada Boeing 767 ran out of fuel. And the pilot managed to glide it for over 100 kilometers before landing like on a little old abandoned airstrip. So essentially there was a couple of minor injuries, but it was very lucky, like there was 69 people on board. And essentially the problem was the fuel manifest was in kilos, but when they were actually refueling the plane, they refueled with pounds of fuel. So 1 kilo is 2.2 pounds. So essentially the plane had less than half the required amount of fuel on it. Very simple error. And it was compounded by the fact that the fuel gauge wasn't working either. So the pilots didn't really know how full the tanks were when they took off. They presumed everything was okay, and then literally mid-flight they ran out of fuel. So only the fact that the pilot was actually an ex-Air Force, Canadian Air Force pilot, and he knew about this old base in Gimli, other than that, the results could have been a lot more horrific. So again, folks, you got to pay attention. Simple errors can be very, very costly. So now we'll just take a wee look. So there's things called dimensions, length, area, volume, and then there's associated units with them. As a scientist, you need to know these. I'm not going to list them all off. Areas of units of area, units of volume, notice squared, cubed, etc. Units of speed, units of acceleration, units of mass. Mass is different than weight. Units of time. So we're going to be talking about the unit side of things in this lecture. We won't get into dimensional analysis or anything like that, which is another branch of this topic, but it's a little bit beyond this module. So essentially, we kind of are familiar with the problems with units. We're members of the EU in Ireland. We use the SI unit system, the metric system. But our closest neighbours on either side both use the imperial system. So in the US and in the UK, they use the older system. So there's a formal set of rules, especially with SI units, and we're going to take a quick look at those. And essentially an easy analogy is different currencies. Different countries have different currencies, and you need to be able to convert your money properly. Otherwise, obviously, there's going to be a financial penalty for you. So as long as we know our conversion factor between the currencies, then we can communicate and trade effectively with our partners. So that's kind of an analogy, but these conversion factors occur nearly everywhere. So some of the main units, well, these are the 7 main units under SI units. The dimension of length, the quantity. The unit is the meter. Mass, the unit is the kilogram. Time, unit is the second. Kelvin for temperature, mole for amount, ampere for electric current, and candela for light. Now in this module, guys, we're generally going to be dealing with these ones. We might touch on this one. We won't touch on kelvins really, but we will do a little bit later on with the mole. So these are the base units, they're called. SI stands for, guys, the Système International. It's French, so it's the International System of Units is what SI units actually stands for. It's adopted around most of the world. Like I said, there's only a few countries now that don't use it. US, UK, Myanmar, and there's another one I can't remember, but there's very few places that actually don't use the SI unit system anymore. Unfortunately, in Ireland, we have two of those countries on either side of our sea border. So the formal rules, guys, this is now just in formal context. So if, say, you're asked to write in SI units, then you must obey these rules. People often kind of circumvent them, but if you're ever writing in an official capacity, say writing a paper for the Irish government or writing your master's thesis or anything like that, then you should always use, if it's a very formal piece of work, you should use the formal rule set. But most people bypass them kind of, so it's a little bit, it can be a little bit vague, but just the main thing is, guys, if you're in a very formal setting, or if the question specifically says use SI units to denote your answer, then you must follow these rules. First one, there's a space between each subunit. So there's always a space. You don't write kg, meter, seconds like that. There's a space between each major unit. There's no space between a prefix in a unit. So say if we were saying a millimeter, well then there's no space there. But there is between the different dimensions. Each dimension gets a space between it. When a unit is derived from somebody's name, we'll see this on the next slide. So if we were talking newtons, if we were going to use the full word, we use a small letter. If we're going to use the symbol for newtons, we use the capital. You don't call newtons like that. You don't use a capital when you're spelling out the full word. Same for joules, watt, hertz. We'll see these guys on the next page. This, guys, is very important, and this is where our negative power can occur quite easily. We don't use per, meters per second, or newtons per meter squared. This is called the oblique. We should use the idea of negative powers. Meters per second should be written as meters per second, like that, using the negative power. Similarly, newtons per meter squared, newtons space per meter squared. So watch for that space, guys. I think there's a couple of questions on Moodle where that might trick you if you're not paying attention. Don't use plurals. So 20 kilometers, not 20 kms. The reason, guys, is because S stands for a unit. It stands for seconds. So if you say 20 kms, you're actually saying 20 kilometer seconds. Here, that statement, 8 milliliter seconds without the space, so it's incorrect on several levels. So just be careful, guys. Don't use an S. S already stands for time, not plural. Now, you'll often see this, guys. You'll see this in your chemistry labs and stuff like that. Like, lecturers often write it, and people write it, but it's only in the very, very formal context that it's completely banned. You will see it, and you will see meters per second written like that all the time. It's just in the very formal context we must use the negative powers. Here's what are called the derived units. Newtons, joules, watts. Notice these are all people's names. These are all famous scientists from throughout history. But when we're describing the unit associated with their name, if we're using the full word, we use a small letter, or we use the capital if we're just using the symbol. Note here, just quickly, guys, force is mass by acceleration. Some of you are doing physics. There's the unit for mass, there's the unit for acceleration. Energy is a force moved through a distance. So it's kilogram, acceleration, and then there's another meters as well. I won't get into it all, guys, because we're into dimensional analysis there. You're not expected to remember these or anything. I'm just kind of laying them out as to show you, first of all, how units are written. They can be very confusing. We prefer to use these shortened, abbreviated versions because they're a lot easier to work with. We won't be using very many of these guys throughout this lecture and the next one. I'm just laying them out there because you will encounter them. So in any kind of an exam or anything like that, you'll always have your conversion factors. So you're not expected to remember these, just you need to know where to find them. So whatever you do, guys, don't go off trying to answer these questions using Google Convert or anything like that, because you will get different answers from the one I'm expecting you to get. The reason is I've kind of rounded a few things up. I've put asterisks on them. But these guys are rounded up just to make the maths easier, considering we don't have calculators. This should really be 39 point, I think it's 787 or something like that. That should be 4.545. But just to make the maths a little bit more doable, I've rounded some units up. Like I said, you'll never be expected to remember these guys. You will be nearly always given them. Some of them, though, guys, you would be expected to remember. As a scientist, you should know a litre is 1,000 mils. You should know a kilogram is 1,000 grams. You should know a metre is 1,000 metres. You'll be expected to know these. Also, that an hour is 60 minutes and 3,600 seconds. So some you would be expected to know, but anything slightly off kilter you would be given. Interesting one for water, guys. 1 gram of water has a volume of 1 mil. Similarly, 1 litre of water weighs 1 kilogram, and then multiply 1,000 litres weighs a ton. So water has a very nice relationship between its volume and its mass. So like I said, you'll be given them. We just have to know how to use them. Now we're going to take a look at the prefixes. Some of these you'll be familiar with. By the end of this module, you will certainly be very familiar with them all. Again, guys, I would usually give you this in the exam, again, because I just want to make sure you know what you're doing rather than struggling over trying to remember various things. Kilo, 10 to the power 3. Mega, 10 to the power 6. Giga, tera. Main thing, guys, is the big ones are on the top. Biggest is on the top. Smallest is on the bottom. And these guys go on like 10 to the minus 24. There's names for them, 10 to the power 24. We just don't need that level for this module. The other thing as well, guys, just to be aware of, is usually in a textbook you'd see these as two separate groups like this. They have the big values and then they have the secondary. But it kind of ignores the idea that that there's this 10 to the power of 0. So say if we were looking at meters, then 10 to the power of 0 is just simply given meter. If we're talking about 1,000 of that, that's a millimeter, centimeter, decimeter, micrometer, nanometer, picometer, kilometer, megameter you don't really come across. But just there is this 10 to the power of 0. This is just for the unit. And that also exists. We might see that not in this lecture, but some of the later lectures. We might need to be aware of this sense of it's a continuum. It's not two separate blocks of units. It's a continuum on a scale, starting with very big and working our way down to very small. All values, though, guys, are greater than 1. Greater than 0. Sorry, greater than 0, not greater than 1. So there's no negative values if you notice on the left. So now we take a look at some problems with prefixes, and I'll kind of talk you through them, and then you guys can have a go at a few yourselves. So convert the following values to the nearest appropriate prefix. We always have to drop down the list, so I'll show you what I mean. So whenever you get a value, you might end up, say, with 10 to the power of 4 as your answer. Then you would always drop down to the next available prefix to describe that unit. We wouldn't go up to mega, we would always drop down to kilo. Say if our answer was 10 to the minus 5, I would always drop down to the next available unit to describe that. So best explain by example. I think we look at the big values first, and then we look at smaller values. Values greater than 1 first. So here, guys, I'll do it slow first, and then I'll work it out quick. If we write this in scientific notation, it's 1.08 by 10 to the power of 11. I hope you'll agree with that. Now, guys, the next available power, we don't hop up to 12. The next available power is 10 to the power of 9. We drop down to 10 to the power of 9. As a result, this value has got smaller by a factor of 100, so this side here gets bigger. So now, guys, I've got 108 by 10 to the power of 9 watts. The prefix for 10 to the power of 9 is giga. So the most appropriate way to describe that value, number 1, is 108 gigawatts. Note there's a space, but then there's no space between the prefix and the unit it describes. So the answer there, guys, is 108 gigawatts. The next one, write it in scientific notation, 6.78 by 10 to the power of 1, 2, 3, 4, 5, 6, 7. Now 10 to the power of 7 doesn't have a prefix, but the next available one is 10 to the power of 6. We always drop down. As a result, guys, because you always reduce the power, you always make the number a bit bigger. So we've divided by 10 on this side, so we multiply this side here by 10. Now, 10 to the power of 6, guys, has the unit of mega. So this value is 67.8 space mega joules. Capital M, capital J. So that's the correct answer for that one. And finally, 22,500 meters. You can do some of these in your head. We'll just go, okay, that's 2.25 by 10 to the power of 4. We want to drop down to the next available power, which is 10 to the power of 3. This side has got smaller, so this side gets bigger. 22.5 by 10 to the power of 3. 10 to the power of 3, guys, gets the prefix a kilo, so this is really 22.5 kilometers. Note again, space between the number and my units, no space between the prefix and the unit. So that's the idea, guys. Always drop down to the next available prefix. We'll take a look at small values now. Same idea. So here, we need to write it. Be careful with these, guys. It's always good to write everything in scientific notation first. My decimal point has to move 4 places. I hope you'll agree with that. And now, guys, we go to our list and we go, well, we always have to drop down the list. So don't think 10 to the minus 3 is bigger, guys. That's a bigger value than 10 to the minus 4. We want to drop down our list to 10 to the minus 6. So this side has got smaller by 10 to the power of 2. So we multiply the other side by 100, or 10 to the power of 2. This side has got smaller, the right hand side has got smaller by a factor of 100. So we simply multiply the left hand side by 100. And this, guys, would be 124. 10 to the minus 6, guys, is micro. Remember your Greek letters, that's mu. Microseconds. So 124 microseconds. The reason why we drop down, guys, instead of hopping back up is if I had hopped back up, this would be 0.124 milliseconds. And we're kind of, now we've got a decimal and a prefix, and we don't really want to be starting with something less than 1 with a prefix. We always want the value in front of the prefix to be greater than 1. So that's 124 again, guys. That's microseconds, a long tail on that mu. Next one. This one is fairly similar, actually. I should have changed that around, but too late now. 5.2 by 10 to the minus 4 joules. Exact same logic. This will drop down to 10 to the minus 6. Multiply by 100 again. So this is 520. I hope that makes sense. Let's get rid of the joule. So this is it in scientific notation, guys. This is it dropped to the next available prefix. 10 to the power minus 6, as we saw, is micro. So this is 520 microjoules. And finally now, this one's going to require a little bit of work. I know it's 2.4 by 10 to the power of minus something. There's 3 zeros, there's another 3, there's another 3. So it's 10 to the minus 9. So in this case, guys, I don't actually have to adjust anything. 10 to the minus 9 is already a prefix. So now I've got 2.4 by 10 to the power of minus is nanometers. So I hope that makes sense, guys. The main thing, always drop down the list to the next available prefix. So now, actually, guys, this should be 13.1. This is the first question. So I will change that. You know the drill. So just have a go at these ones then. Exact same idea. And I'll just push on then into the next topic, which is conversions. And this, guys, now is where we're beginning to kind of move from one unit to another. So things we need to know, we always need a conversion factor. We discussed those. These kind of ones, 1 mile is 1.6 kilometers. We also need to understand, remember, the term reciprocal. So if my number is 2, its reciprocal is a half. 5 is 1 over 5. We've done this before. 2 over 7, flip it, we get 7 over 2. So remember, any whole number, guys, can be written by a reciprocal. Just write the whole number over 1 and then flip it on its head. And that gives us the reciprocal. So now we're going to see where the reciprocal actually has a role to play. Probably one of its most important roles, I would argue. And say we're given this conversion factor. €1 is 80 pence sterling. And we're asked to convert from euro to sterling. So this, guys, is a really important concept. So just kind of pay attention to this. If we're going with the conversion rate, we're given 1 on the left and we're changing it into sterling. We're given €1 on the left, we're changing it into sterling. That's what we're asked to do. Change from euro into sterling. If you're going with your given conversion rate, then, guys, you multiply by the conversion factor, which in this case is 0.8. If we need to go the other way, if we need to go from sterling to euro, we're going against the conversion factor we were given. In that case, guys, we multiply by the reciprocal of our conversion factor. Now, effectively, it ends up means that you divide by the value, but we need to keep this idea of reciprocals, guys, for when the maths starts getting a bit tricky and we're doing several conversions in a chain. Then you need your reciprocals to keep your maths proper. So we'll take a look. Convert €100 into sterling. Well, we're asked to go with our conversion rate. We know the conversion factor we're going to be, because we're going from euros into sterling, the same way as our conversion factor has it. Then, guys, we simply multiply by 0.8. So in this case, I'm going to have 100 euros is equal to 100 by 0.8. So in this case, that's going to give me 80 euros sterling. So really, guys, €1, just to be clear, €1 is 1 by 0.8. And then we can just multiply both sides. Sorry, that's meant to be a sterling sign. Then we can just multiply both sides by 100, and we get our answer then of 80 sterling. 100 euros is equal to 80 sterling. Now, going back the way, well, what if we need to convert 100 sterling into euro? Now, guys, we're going from sterling into euro. We're going against our conversion rate, so we use our reciprocal. So £1 sterling is equal to 1 over 0.8 euros. And once we have that, guys, we can answer any question, because now we just multiply both sides by 100. So this will become 100 over 0.8, multiply top and bottom by 10. We have 1,000 over 8, which works out to be 125 euros. So the main kind of lesson here, guys, is if you're going with your conversion rate, your given conversion rate, you multiply by the conversion factor. If you're going against your given conversion factor, you multiply by the reciprocal of the conversion factor. Look at another example, again with money. €1 is now worth $1.20, different currency, same idea. If we're going against our conversion, if we're going from dollars into euros, then we multiply by the reciprocal of the conversion rate. And we'd see this here. Convert 100 euros into dollars. We're going from euros into dollars. That's the way the conversion is set up. So now we would just say, well, €1 is $1.2. Sorry about my crappy dollar sign. And now, guys, simply multiply both sides by 100. I'll make that look a bit better. And we get $120. I think you'll agree with that. If we need to go against the conversion rate, convert $72 into euros. Well, now, guys, we are going against the conversion rate. We're going from dollars into euros. So we multiply by the reciprocal. So $1 is equal to 1 over 1.2 euros. We multiply both sides by 72. This, guys, will become 72 over 1.2. Dollars, euro, euro. And now, guys, multiply top and bottom by 10, 720 over 12, and we'll get 60. So $72 is 60 euros. And again, now, guys, there's loads of questions on Moodle. This should be 13.2. Sorry, I forgot to label those in. So now have a wee go at these ones. And again, guys, if you do find these confusing, there's videos on Moodle, there's notes on Moodle to help you through them as well. This is definitely an area where students struggle, but everyone struggles with conversions, guys. Engineers, scientists throughout the world struggle. As we saw with the Gimli glider, it's an easy mistake to make. So just have a go at those. The main thing, guys, you're asking yourself, am I going with the given conversion rate or am I going against it? And that determines the appropriate conversion factor to use. Remember, guys, that's 13.2. Okay, so now we're going to take a look at multi-step problems. And in these problems, guys, there's nothing new. It's just we often have to chain together conversion factors to arrive at the solution. So we'll take a look. And so say we're given €1 is 80 pence sterling and €1 is $1.20. Here in the question we're asked to change $360 into sterling, but we've no conversion rate for sterling, for dollars into sterling. We don't have that conversion rate in our list, but what we can do is go from dollars into euros, and then we can go from euros into sterling. So our first step, we're going to go from dollars into euros. We're going against our given conversion factor. So the first step, guys, to get from dollars into euros, we need to multiply by this conversion factor here. Then the next step, guys, we want to go from euros into sterling. We're going with our conversion factor. So we multiply by 0.8. So now we actually just multiply these two together. Remember, top by top, bottom by bottom. The conversion factor, guys, to go from $1 into euros is this much. So that's the conversion factor for dollars into sterling. We do a little bit of maths on it, multiply top and bottom by 100. To move the decimal point, we'll have 80 over 120, cancel top and bottom, and that comes 3/2. So that, guys, is the conversion factor to change dollars into sterling. So now we can say, well, $1 is this many sterling. And now just multiply both sides by 360. 360 by 2/3, you can cancel, divide by 3, get 120, multiply by 2. So $360, guys, is £250 sterling. So you can see what I mean, guys, is we have to chain together our conversion factors. And obviously I could have the South African rand tacked on again, so we'd need a conversion factor from sterling into rand, etc., and we'd multiply again, but we haven't developed a problem to that level. Just a similar example, just going back the way. We need to convert sterling into dollars. So we're going to go first of all into euros and then into dollars. So sterling into euros. We need to use the reciprocal. And then, guys, we're going from euros into dollars. We multiply our two conversion factors, top by top, bottom by bottom. We get this. Multiply top and bottom 100, just get rid of our decimal, tidy up. And this is our conversion factor. And you can see, guys, it's the reciprocal of the previous example, which should make sense. In the last example, we were going this way. And now we're going this way. So the last example, to go from dollars to sterling, the conversion factor was 2/3. So it makes absolute sense to go the other way. We use the reciprocal. We take a look at £1 sterling. And you could work it out, guys. £1 sterling is $1.50, but I want to keep this conversion factor sitting here all the time. Multiply both sides by 120 as the question asks. Divide by 2 first, we'll get 60. Multiply by 3. So £120 sterling is $180. We look at one more, guys, because these are quite tricky and there's quite a bit of skill involved. Convert 80 kilos into stone and pounds, and here's our conversion factors. So we need to go, guys, now there's not too many routes in this one, so we're going to go from kilo. Sometimes, guys, there's several routes to get to your answer, as you'll see when I give you the next set of problems. Whichever route you choose is valid. It just, you might end up with slightly different conversion factors as you go along, but you should end up with the same answer. We need to go from kilograms, guys, into pounds, and then into stones. So kilograms into pounds is straightforward. And then, guys, we need to go from pounds into stones. So we need to use the reciprocal of our conversion factor, which looks like this. So there's my conversion factor now. I multiply these two together, top by top. I hope you'll agree, 1 kilogram. This is my conversion factor to go from kilos into stone. Multiply both sides by 80. Now 80 by 2.2 is 176. And now, guys, this is where we need to be careful. So I'm just going to take it from here and we'll work our way out. So we need long division. We have 176 divided by 14. Now, what's really important here, guys, is a very important concept, is we're moving into an imperial measurement, stone. I've just wiped everything out. It's not metric. So generally, guys, we don't use a decimal point. You shouldn't use decimals in the imperial system because they're not metric. The imperial system isn't divided into nice factors of 10. So the metric system is inappropriate when we're describing imperial units. You'd never go into a woodyard and ask for, say, 6.5 or 6.32 feet of wood. You'd always say 6 foot, 4 inches, and 3/8. So it's inappropriate, guys, to use decimals when we're talking about the imperial system. Now, it does occur, I'm just kind of trying to give you the formal things, but it does occur on occasion. But just to be aware, in general, if you're using the imperial system properly, you do not use decimals. So this is what we have. And the answer actually drops out quite neatly because of this. So we want to figure out, well, how many stone do we have first of all? Well, 14 won't go into 1, but it will go into 17 once. We'll subtract. The 6 drops down, and now we're saying, well, 14 into 36. It won't go in 3 times, that's 42, but it will go in twice. So 2 by 14 is 28, and we subtract, and we have 8 left over. And this is actually our answer, guys, even though you probably don't realize that our answer is now looking at us. We have 80 kilos is 12 stone and 8 pounds left over. And there's our answer. So I hope that makes sense, guys. It's very important with imperial systems to try not use decimals. Now, it does occur. I'm not saying it never occurs, but to be formally correct, you wouldn't use decimals with the imperial system. With the metric system, that's what the metric system was designed for. Everything is nicely divided by 10 in the metric system. That's why it's so universally popular. So there's our answer there, guys. I'll just leave this slide up. And now this should be 13.3 for you guys. Apologies about that. Pause the video. And have a wee go with these ones. And these will take a little bit of time, guys. So just take your time, work your way through them. And don't use Google Convert. Okay, folks, so I'm just conscious of time. We just run slightly over 14 minutes. So I just want to finish this up. And thank you for listening. Much appreciated. We'll see more again in lecture 14.